5 minutes to understand the University of Twente's open source real-time CEINMS-RT computational model. Have you ever wondered, is there a way to see in real time how your muscles contract, how forces travel through your body, and how each joint bears its load as you take every step? In sports science, rehabilitation medicine, and exoskeleton engineering, this has long been a tremendous challenge. In the past, researchers could only analyze human movement offline in the lab, using motion capture and force platforms to compute internal biomechanics. A single movement could take minutes, even hours, to process. Clearly, such methods are not suitable for situations that demand immediate response, such as exoskeleton assistance, neuroprosthetic control, or dynamic rehabilitation assessment. This raised a fundamental question for scientists. Can we compute the internal physiological state of the human body within milliseconds? The framework introduced in this paper, CEINMS-RT, was created precisely to answer that question. CEINMS, short for Calibrated EMG-Informed Neuromusculoskeletal Model, is a physiological modeling framework that combines electromyography with musculoskeletal dynamics. Earlier versions of CEINMS were highly accurate, but far too slow for real-time use. The RT in CEINMS-RT stands for real-time. The goal of this study was to transform CEINMS from an offline analysis tool into a real-time human-machine interface, allowing the computer to complete an entire muscle-skeletal computation within milliseconds as the person moves. Simply put, it used to be post-game video analysis. Now it's real-time coaching through your earpiece. So, how does CEINMS-RT actually work? You can think of it as an internal biomechanics engine for the human body. When we move, surface EMG electrodes capture the electrical activity of our muscles. These EMG signals are processed, filtered, rectified, smoothed, and then sent into the CEINMS-RT core model. Inside the model, each muscle has its own physiological identity. Its maximum force, tendon slack length, and force length relationship are all individually calibrated according to the subject's anatomy. The model then uses the strength and timing of EMG signals to calculate muscle activations. Through a hill-type muscle model, these activations are translated into muscle forces. Finally, by combining all muscle forces through a moment-arm matrix, the system computes the real-time joint torques. Though this process sounds complex, in CEINMS-RT it all happens within 13 to 17 milliseconds. In other words, the system can reconstruct the internal biomechanics of the human body 60 to 80 times per second and output the results in real time. To test its performance, the research team recruited 5 healthy male participants. Each performed 3 types of movements in the lab: steady walking, sit-stand-squat transitions, and single-leg lifts. Their kinematic data and surface EMG signals were recorded simultaneously. The data were processed by 2 models, the traditional offline CEINMS and the new real-time CEINMS-RT. The researchers compared the outputs, including muscle forces, joint torques, and overall metabolic trends. The results were remarkable. The real-time system's outputs nearly overlapped with those of the offline model. Joint torque correlations reached 0.94 to 0.98. Muscle force errors were only 6% to 9%, and computational speed improved by hundreds of times, from minutes down to just milliseconds. In short, CEINMS-RT achieved almost the same precision as the offline model, while being hundreds of times faster. The importance of CEINMS-RT lies not only in its technical breakthrough, but in how it provides a new interface for human-machine cooperation. In rehabilitation medicine, it enables real-time assessment of muscle recovery and adaptive adjustment of training assistance. In exoskeleton control, it serves as a physiological control core, allowing robots to interpret muscle signals and deliver assist-as-needed torque. In sports science, it can monitor athletes' muscle loads during motion, providing physiological insight for fatigue assessment and training optimization. Even in virtual reality and digital twin applications, CEINMS-RT can act as a human biomechanics engine, giving virtual avatars realistic muscle responses. The emergence of CEINMS-RT marks the moment when neuromusculoskeletal modeling truly enters the real-time era. For the first time, we can see, within just a few milliseconds, how muscles generate force and how joints respond. If you enjoyed this, don't forget to like and subscribe so you won't miss more amazing robotics.